order derivative test is not necessary here. Because there's only one critical point. There's no way you can achieve the maximum right here. So in the very last example, I want, any questions here? Any questions for this particular example? This is actually a very, very popular example. Okay, so very, very popular question. So when I say popular, you get a hint, right? It is an extremely popular question. There are essentially just one principle here, which is finding a critical point. But you need to transform the problem into such optimization question, right? You have to translate this problem into an optimization question. As long as you can do that, the following is just a matter of taking derivatives. So in the very last question, I want to mention one more restriction on these optimization questions. So I have a function f(x,y) is equal to x squared plus y squared minus 6y plus 9. And I also have a domain of this function is equal to x squared plus y squared is less than or equal to 25. So I want to find all the local extreme values as well as the global extreme values. Up to now, okay, listen carefully here. Up to now, all we did is to find and classify the critical points. As long as you are using second order derivative test, you're only getting it as a local maximum minimum. We haven't done any global yet. One big problem about the global extreme values is in some cases the global extreme values do not exist. For instance, here, the global minimum will exist at this given point. You can achieve the shortest distance. The global maximum does not exist at all, right? Because you can make your distance as large as possible by moving to infinity. So the global maximum does not exist. However, if my domain is a bounded domain, this is indeed a bounded domain, right? What is this domain?
Circle radius 5.
A disk with center 0, 0, radius 5, right? So this is a bounded domain. As long as it is a bounded domain, you will definitely achieve all the global extreme value as well. Here, the domain is not bounded. I can achieve the global minimum. I can also achieve the global maximum. Okay. So the way of getting this is we have to distinguish two things. First one is the local thing. So local minimum and maximum, which is exactly the same principle as what we did over there. One complexification coming from this bounded domain is the boundary. All right? I can only find the local maximum and local minimum if the point is in the interior. I have to also compare these values with the boundary values. So basically, this is what we're going to do. We have this bounded domain. I need to find all the critical points. I need to classify whether it's local maximum or local minimum. And then I need to find its boundary values, how the function will achieve their values on the boundary. The boundary is actually x squared plus y squared is equal to 25. Okay? So I will quickly go through this easy case. So let's quickly find all the critical points. Fx is equal to 2, x is equal to 0. So x is equal to 0. Fy is equal to 2y minus 6 is equal to 0. So y is equal to 3. All right? So there's only one critical point coming from here. So it's 0, 3. Not only this, I know 0, 3 is indeed in the interior. All right? So this is the square root of 5. So 0, 3 is right here. Okay? So the function value at this point is f0, 3 is equal to 0 plus 9 minus 18 plus 9 is equal to 0. Okay? So this is the function value at its critical point. All right? So 0, 9 minus 18 is equal to 0. I want to answer whether this 0 is a local maximum or local minimum by second order derivative test. Second order derivative test, fxx is equal to 2, fxy is equal to 0, fyx is equal to 0, fyy is equal to 2. So this is my matrix. The determinant is positive, first entry positive, so 0 is a local minimum. So it's a local minimum. But I'm not sure whether this 0 is a global minimum yet. I do not know whether this is a global minimum yet. In order to do that, I need to find the function value on the boundary. The function value on the boundary is this function with the restriction x squared plus y squared is equal to 25. Right? So on the boundary, I can indeed immediately eliminate one variable x. You see that? So x squared is equal to 25 minus y squared. So I plug in this equation, I'm getting a function involving only y. So if I combine these two together, I'm getting equation 25 minus y squared plus y squared minus 6y plus 9 is my new function here. I'm going to call this function g of y, which is equal to 34 minus 6y. Okay? 34 minus 6y. Am I making any mistake?
Shouldn't the 25 and the y squared be squared? Because the x squared, shouldn't the whole thing be?
Not really. I'm only replacing x squared, right? I'm only replacing x squared by 25 minus y squared plus y squared minus 6y plus 9. Yeah, this is the function. Where my y is changing from minus 5 to 5. Okay? So if y is changing from minus 5 to 5, you can actually achieve the minimum value on the boundary. Okay, I'm sorry, I'm borrowing some minutes or figures. So if y is getting a 5, I'm getting a minimum value here. Right? So g of 5 is equal to 34 minus 30 is equal to 3. G of minus 5 is equal to 34 plus 30 is equal to 64. So now my principle says if I want to find a global extreme values, the three candidates are 3, 64, and 0. The smallest one is going to be the global minimum. The greatest one is going to be the global maximum. So global minimum is 0 indeed. It is not local, but also global. Global maximum is 64. Okay? So when you have boundary, the only complexification comes from here is you need to not only find all the critical points, but also find the boundary. Okay? So next Monday, I plan to review chapter 4.